We can see here the different phases we talked about. Okay, so mainly this is phase 1, where we have increase in temperature of ice from -20 to 0. In the second phase, we have melting, which takes place at constant temperature. So we have, in this phase, we have mixture between ice and water. At this point, we have 100% ice. At this one, we have 100% water. And anywhere in between, we have a composition of both. Now, in the third phase, we have water phase, okay? But the increase in temperature is due to the gain of sensible heat. So we will increase at a certain slope. And to calculate the slope here, to find the slope of your curve, you should go back to the formula. The formula is Q equals to, as we said, MC times delta T, okay? And since we are representing here the variation of temperature with respect to, here in this graph, to make it general, okay, we divided delta Q per the mass. Because if you divide per the mass, you can use it for any mass by just, guys, please mute your microphone. So Q is equal to MC delta T. So if we take M to the other side, you have Q over M is equal to T times dt. Okay? So you are representing the variation of temperature with respect to Q over M. So to find the slope of your curve, you have dt is equal to Q over M. So dt is equal to Q over M times 1 over C. So you can say that this term 1 over C represents the slope of your curve. And since the specific heat of water is the highest one between specific heat of ice and steam, you can deduce that the lowest slope will be the slope of this line, while the slope of ice and the slope of steam is higher, okay? This is why if you represent the variation with time, you can see that, because if we consider that we are providing heat at a uniform rate, so for a certain period of time, we are providing the same amount of energy. You can see that the increase in temperature in the ice and the steam is much faster than the case in water, okay? Due to the high specific heat of water. Okay, so if you draw T with respect to time, you will see that temperature of water increase of ice increase in a faster way than water, and the faster increase will be in steam because steam is characterized by the lowest specific heat. Any question on this problem?
No.
Okay. Guys, some of you didn't give me their project, so please try to decide on the project soon, okay? Because from now to 1 month, we will start to do presentation of projects. Now we will move to another example, which consider conduction. The wall of an industrial furnace is constructed from 0.15 meters thick fire clay brick having a thermal conductivity of 1.7 watt per meter Kelvin. Measurements made during steady state operation reveal temperatures of 1400 and 1150 Kelvin at the inner and outer surfaces respectively. What is the rate of heat loss through a wall that is 0.5 times 1.2 meter on a side? So here you have heat losses through the wall because the inner temperature is higher than the outer temperature. So they gave you the temperature of the inner side, it's 1400 Kelvin, and the temperature at the outer side is 1150 Kelvin. And they gave us all properties we need. We have the thermal conductivity of the material, it's 1.7 watt per meter Kelvin, and we have the thickness of the wall. Now, since the thickness of the wall is much smaller than the length of the wall and its height, we can say that its we can approximate conduction to be one-dimensional, okay? Because conduction is mainly given by the following: Q is equal to K times A times dt, okay, over thickness. Now you can tell me why conduction will not take place, for example, in the following directions. Why only in this direction? Why only in this one? Because first, in these directions, you don't have change in temperature. So you don't have delta T. Okay? Mainly delta T is between these two sides. So conduction will take place between these two. And also the thickness here is much smaller. So lower is the thickness, higher is the rate. So in all cases, the dominant direction will be this one. Okay? Because in this direction, you have large variation in temperature. And this large variation in temperature is taking place for a very small thickness, which will increase the rate of conduction. Okay? So here it's good to consider that it's 1D conduction, because the temperature variation is nearly in one direction, which is characterized by a small thickness. So to find the conduction flux, it can be treated as 1D case. So it's K times A times dt by dx. Okay, here minus K times minus Ka dt by dx. But you know that, so I will write it here. It's minus Ka dt by dx. Okay, but we have seen that because it's 1D and because so it's only along one direction, it's restricted to this term along x, and you have constant conduction coefficient K. You have steady state, so you have steady state conditions here. It's equal to a constant, and because it's a constant, so dt by dx is constant. This is why we can say that the variation of conduction is linear. Okay, and we can replace dt by dx by T2 minus T1 over L. Okay, but since we have a minus, because in the expression we have a minus dt by dx, when we replace in the equation, we have T1 minus T2 over L, because it's minus dt by dx. So if we go back to the heat flux, it will be equal to Q equals to K times A times T1 minus T2 over the length L. And here everything is provided, okay? For what will be the cross-sectional area for heat transfer? Heat transfer is going through which area? What is A here? Who will tell me?
W times A.
Very good, because you will take the area that is perpendicular to the heat flux. If you look at the 3D figure here, the heat flux is crossing over the following area. This one, okay? This is a rectangular area, and it's equal to the height h times the width w, okay? So A is simply, so we replace A here by h times w, and please pay attention for your units, okay? So they gave you Kn, since K is in watt per meter Kelvin, then you will use for A meter square, for T you will use Kelvin, and for L you will use meter. In this problem, because you have delta T, it's not wrong if you use T in degrees, okay? Because T1 minus T2 in degrees is equal to T1 minus T2 in Kelvin. But to be on the safe side, always use Kelvin, okay? Because we will see that in radiation, for example, you cannot use degrees instead of Kelvin, because you don't have a difference in temperature. You have T to the power 4. It's not like here T1 minus T2, okay? So when you have radiation, you should use Kelvin instead of degrees, okay? Any question for this problem? So here you have the solution, okay? Now, sometimes they ask to find just the heat flux per unit area, okay? So they can tell you what is just the heat transfer per unit area, then you do K delta T over L only. And if you want to find the heat loss, the total heat loss, not per a certain unit area, for the total area, then you multiply by H times W. Okay? So you should look at the question. What is the question that is required from you? It is the total heat to calculate, or it is just the heat flux per unit area? Now, we will consider an example where we have a mixed transfer by conduction and fusion. Okay, so in this problem, we will see how energy can be transferred by conduction in order to, let's say, be transferred into latent heat. So large fuel cells, such as those used in automotive applications, often require internal cooling using pure liquid water to maintain their temperature at a desired level. In cold climates, the cooling water must be drained from the fuel cell to an adjoining container when the car is turned off, so that harmful freezing does not occur within the fuel cell. So this is an interesting application where you have, for your car, you don't want the cooling water to freeze. So you have some strategies to heat it continuously in order to avoid formation of ice. So consider a mass M of ice that was frozen while the car was not being operated. The ice is at the fusion temperature, which is Tf equal to 0 degrees, and is enclosed in a cubical container of width W on a side. Consider the cavity of width W equal to 100 millimeter on a side, the wall thickness to be 5 millimeter, and thermal conductivity K to be 0.05 watt per meter Kelvin, while the outer surface temperature is 30 degrees. The density and latent heat of fusion of ice are given. So here what is happening? Let us look at the figure. We have a small part of ice that was formed inside the water. And what we don't want to be, okay, is to have ice to remain in the water. So we want to heat it in order to transform it again to water, because this water will be needed to cool our car system. Okay, so what will happen here? This part of ice will be inserted in this cube. Okay, this cube is of length W for each side, and we have this cube is characterized by a certain thickness. Okay, and we are exposing the outer temperature of the cube to a temperature of 30 degrees. So the outer surface is exposed to a temperature of 30 degrees in order to transfer heat to the inner side of the cube and to melt the ice. Okay, so here mainly what is happening, I am converting heat which will go through conduction inside my cube into latent heat that will melt the ice. Okay, so here, because the conduction heat is only used to melt the ice, I can say that Q of conduction, okay, will be equal to Q absorbed by ice, because here we have only the ice piece, so it will absorb the heat provided by conduction. So what is needed is to find the time which is needed to melt the ice. So how much time I need to melt this mass of ice? So let us write the expression of Q conduction and Q ice and decide on the time needed to melt my ice into water. Okay, so first Q ice in joule. Okay, how to find Q ice in joule? What is the heat required to melt this part of ice?
It's the latent heat.
It's the latent heat. So it's the mass of ice. Okay, so now I will assume that I don't have given. I will express function of my variables, and once I have the given, I can replace back. So let's say they tell me the mass of ice is, let's say, 10 grams, I can replace. Okay, now I will do it in general. So I have, it's M times the latent heat, okay, of melting. I will call it LM, latent heat So let us put here of melting. Okay, this is the unit here for M will be in kilogram or gram. Okay, but if this is in kilogram, L will be in joule per kilogram. Okay. Now, what is the expression of heat for conduction? Q conduction. What is Q conduction?
It's 6 times Ka delta T over L.
Only
على فكرة والله يعني هلا لحاله طفى الكمبيوتر رجعت دورته.
Can you please mute, guys? Can you please mute your microphones? Okay. One of you told me it's 6A times K times dt by dx. What dt by L, if you want, which is the thickness. Okay. Why is this missing? One term is missing. What is the missing term here? First, why it's 6A? Because it's a cube, okay? And conduction takes place over the 6 sides, okay? This is why it's 6 times the area of each side, and the area of each side is W squared, okay?
In
So,
mass, you think?
no, not the mass. Look, when you do 6A times K times delta T over L, this gives you what? What is the unit of this term? This is the conduction flux. The conduction flux is Q dot, okay? This means that the unit is in watt. But what you want is to find the total heat in joule. If you have the heat flux in watt, how you transfer it to joule? What should you do?
Times time.
You divide it over time.
You should multiply it by time. Multiply.
Sorry, yes.
Because what is joule per second? Okay. So in order to find the total amount of heat delivered, it's the heat flux, okay, or the heat rate times the time. Okay. So the heat rate, which is the heat provided per unit time, we multiply it by the time, we get the total heat provided. So we can say that to melt ice, Q conduction should be equal to the latent heat of melting. So now we can put our equation. The condition is the M times L is equal to 6 omega square times K is the conductivity times, what is delta T here? What is delta T in this case?
0.
Delta T.
لا delta T less surfaces هاي.
Yes, delta T for conduction. Look, the conductive flux is going from the hot surface towards the cool surface. The inner surface is in contact with ice, so it will have the same temperature of ice.
No, it's
Okay.
only T1.
Yes, so it's equal. Look, because look, if you have here ice, okay, this is the piece of ice. Even if you have water around it, whenever you have still a certain percentage in ice form, then the whole system will be at the same temperature of 0 degrees. So the temperature on the inner side of your cubicle chamber is equal to 0 degrees, and the outer temperature is 30. So delta T from hot to cold is 30 minus 0 over the thickness of the wall F. Okay, so now and we don't forget to multiply by the time. So now we can get the expression of time. Okay, just do not confuse this L. This L is the thickness, and this is the latent heat of, I will put melting, Lm. Okay, to not forget. So now if we look at the solution, so as we said, first the conduction rate is constant because here it's steady state conditions. The inner and outer temperatures are not varying. So it's K times the total area, 6W squared times delta T over L. and the amount of energy that is flowing inside the system is the rate times the time, okay, which is T, the time needed for melting. Now, this energy is absorbed in form of latent heat. So I can say that the energy is used to melt my ice. So it's equal to the mass of ice times the latent heat of melting. So now if I replace, if I put them equal to each other, I can derive the expression for the melting time. It's equal to the mass of ice times the latent heat of ice times the length of the thickness of my walls over 6W square K delta T. And now in this problem, they gave me all the information, but they didn't give me M directly. How can I calculate M? They didn't give me, look, they gave
From the density?
Yes, very good. They gave me the density, and what is the volume occupied by water or ice here?
Side cube.
It's the volume of the cube, okay? Because the ice-water mixture is filling my cube. So to find its volume, it's equal to, look, each edge here is W. But what I am interested in is this length here. So what will be this length?
L minus 2T.
It's W minus 2L, okay? Because L is the small thickness and W is the length. So each side, from the inner side, it's W minus 2L. This is why the volume of the water-ice mixture, so V of water-ice mixture, is equal to W minus 2L cube. Okay, so now if I replace in my expression, I put the mass is rho of my system, which is given to be 920, times the volume, which is W minus 2L cube. I find the mass and I replace in my equation the different terms. I get the time for mass. Okay. Any question for this?
No, thank you.
Okay. Can you please try to solve the remaining problems, and next time we will solve them together. Okay. And if you need any question, you can chat me using WhatsApp anytime you want.
Thank you so much.
Welcome.
Yeah.
Bye.
Thank you.